So stack area is an area of memory for storing temporary values. So this example with the return address used by, generated by the call and used by the return instruction is a good example of a temporary data, because this return address is needed only as long as we're running this procedure, and when we return, we no longer need this value. So that's example of a temporary value. Unlike other segments that store data starting from low memory, the stack stores data starting from the high memory. So let's just demonstrate this. Basically, when I draw this box with that is given to the stack area in our program, and it's configured by the program loader of the operating system. This was the reason showing you from the high memory that I consider that our memory addresses go like this: 0, 1, 2, 3, 4, 5. So this is the low addresses right here, and here we have the high addresses. So this is why when I was drawing my diagram for location of this return address used by the return instruction, I placed it right here in a high memory, not in the low memory, but here. My return address was shown right here. Okay, so we'll be able to talk about the return address and this idea of using high memory first and then going towards the low memory when we begin to consume memory in the stack area. We'll be discussing it a little bit later on. We typically refer to, as we talk about the stack, that we typically say that we push into and pop from the stack. Use this memory as a stack. So the stack gets its name from a similarity of the spring-loaded plate holders in cafeterias. So let's just talk about this. So the analogy is that we have this holder of plates with the spring, and we can store plates in the stack. So we can have some plates loaded onto the stack right here, and the whole idea is that you can only manipulate the stack from the top. Okay, so when you put something on the stack, when you push, it remains on top, and you can actually use it, because when soon we start talking about ESP register, it will be pointing always to the top of the stack. And you can remove values also only from the top of the stack. So here, as we say that if, for instance, we need to remove this third plate, we would have to remove this one, and then we can get to the third one, because then it will be on top of the stack. So this type of organization of stack is called LIFO, or last in, first out. So last in, first out. Program continually uses the stack to temporarily store and preserve return addresses, procedure arguments, memory data, flags, and registers. And I also would add to this list local variables. So when you write your C code and you use local variables inside your functions, well, guess what? They are organized somewhere in the stack area, and the placeholder for each function call is called stack frame. In Unix environment and Linux, it's also known as activation record. So it's the same thing: activation record for procedure or function call, or stack frame is where the local variables reside in a C program when we call a C function. So we discussed briefly already the workings of our stack instruction. Let me just preserve this in case we need to use this example later on. I'm just going to save this the two of these lines in my notes. I'm going to say debug, stop debugging. and these are my notes. So somewhere we have seen that the call was made into our main procedure, and we were able to trace return into the next instruction that followed the call, right? So return took us right here. So I just want to preserve this in my notes. Okay, so the stack is assembled okay, so the stack is assembled in as an initialized segment of a finite size. So that's why it's possible to specify the stack size, but it's a limited size. If we want smaller program, we can generate a smaller stack if we want, but we can also make it larger, like 4 kilobytes right here, using the stack directive. The operating system initializes ESP to the address of the first byte above the 4096 in this example bytes in the stack. So first byte above. So what it means is this, that this is our stack, okay, and this is our ESP register, and this ESP register is pointing the program loader of the operating system, leaves it just before calling main. It sets it up and has that ESP register contains the address of this thing just below our stack. So this means that as soon as we begin using the stack, the ESP will be moved to this location, and we start using the stack area as prescribed, and this is now we begin using the stack as expected. If we save more things on the stack, of course ESP will be moving in this direction, and we say that if these are the low memory addresses and these are the high memory addresses in this area, we say that stack grows in the direction of low addresses, and it shrinks in a direction of higher addresses. So when we push things on the stack pointer always indicates the last element that was saved on the stack or pushed on the stack, and it keeps growing in the direction of lower addresses. Okay, if we reach this limit right here and we try to push even more, we'll have CPU will generate a stack overflow exception, which will basically terminate current execution of the program and not notify the operating system about this type of offense. That program has to basically run out of stack space, and it's not something that is permitted. So we should be careful not to overrun or overflow the stack space. So larger or smaller stack can be allocated depending on the anticipated usage of the program.